the NAGROM's seminar. It's a happy Valentine's Day to everyone. It's a great pleasure to introduce Professor Singler, John Singler. John has been working in reduced order modeling for quite a while now. He made fundamental contributions to the numerical analysis of proper orthogonal decomposition, but he had, he's done work in a variety of reduced order modeling, control, numerical approximation areas. Today, it's a great pleasure to have John give a talk on data approximation capability of POD. I'm gonna let John, take over. And he said that it's okay if you have questions along the way. You can raise your hand. I'll try to check this and then let him know. You can ask the question before the end, and of course at the end we'll have some more questions. Okay, John, floor is yours.
All right, thank you, Tryon. All right, so it's a great pleasure to be here. And I wish I could be here other times. Unfortunately, I teach, I was telling everyone before it started, I teach at this time normally. So unfortunately, I cannot make it. This seems like a great seminar series, but today I'm here. So yes, and thanks to the seminar organizers. This is a great seminar, and I appreciate the invitation. So I'm going to talk about work with a bunch of different collaborators, some of whom are here. So a couple of my PhD students, former PhD students now, and thanks to NSF, right? So let's see. So I know I don't think maybe to give much of an introduction, but I'll give a little bit. I don't know there could be, I don't know. So I'll give a little bit just feel free to stop me if there's questions along the way. So, all right. So I will mostly talk about POD in the context of model order reduction for partial differential equations. Of course, it can be used in many other situations. And the idea, right, very brief idea, is to use either simulation or experimental data to produce POD modes, and then use some Galerkin projection or modified thing to reduce down the governing equations so you can do something with them quickly, either control, simulation, optimization, whatever. So I would still say we don't understand these reduced order models very well. So they can sometimes work incredibly well. It's sometimes surprising how you can take a full order model of millions of degrees of freedom and reduce it down to 100 and get the kind of the large scale behaviors and capture them. And then sometimes they just can fail dramatically. We want to be able to predict the accuracy of these reduced order models, and that's one of I think the ideas of this whole seminar series is to try and look at the numerical analysis of these things and attempt to get it up to more of the level of the more traditional numerical methods like finite elements, which have much more robust or much more well understood, right, numerical analysis. So of course, with POD, I think we can safely say, as far as I can tell, numerical analysis is really only about 20 years old, which in the time scale of math is like a few seconds. So I mean, but anyway, so I think we can start with with Kunish and Volkwein's work, literally just about 20 years ago, and they looked at bounding the error between right solutions of some parabolic PDEs, the Navier-Stokes equations, and the reduced order models. So something they did, and that has been mostly done since, is they assumed all the initial data and the parameters are not varied in the reduced order model. Of course, in applications, this is not satisfied, but they started here because we want to get some idea of how these reduced order models perform. And as soon as you vary these things, the numerical analysis becomes much more well, much more difficult, right? Of course, there is work in that area, in that direction. That's not something I'm going to talk about. All right. So I'm going to go in this direction. So, of course, many people, including many here, have looked at extending their initial works in many different directions, modified model order reduction schemes, different PDEs, different numerical methods to collect the simulation data. Ultimately, all of these results rely on the data approximation capability of POD, both very old results and newer ones. And so, my goal is to survey all of this. I'm going to only briefly highlight how these data approximation results connect to the numerical analysis. I want to mention some open problems. So maybe this talk will be a bit more on the theoretical numerical analysis side of things. I don't know. I figure we have to, well, at least I've always been, for some reason, interested in these questions. So in any case, I'm also interested in the computational side of things, but I won't talk about that today. So, all right. So to start, we'll go just briefly give some basic ideas here. So I'll have W, or whatever you want to call it, be your PDE solution, or whatever the full order model is. And then WR would be the solution of the reduced order model. The very typical numerical analysis approach, even back to finite elements or whatever else, is to split the error in this additive fashion. So you split it into two pieces. Rho R there is the solution data minus some projection of the solution data. And that is a projection that's built with POD. I'll talk about those. So rho R there is what we will focus on. The other quantity theta lives in the reduced order space, and that is typically bounded using error estimate approaches that are similar in some sense to type of finite element error analysis and other things. Of course, there are many differences. However, but typically, some norm of theta R is going to be bounded above by these data approximation errors, or norms of them, or quantities involving rho R. So that's what I'm going to focus on, and various other topics. Okay, so all right, and this is flipped in a sense from finite elements, where rho R is typically very well understood. Right. That the projection there could be some interpolation or whatever, and you have global estimates for whatever W is, as long as it has some regularity properties, everything about rho R and all sorts of norms and things like this. That is POD is flipped, right? We know very little about this. Relatively speaking, we have no global results at all. In a sense, they're all local. And I'll talk a little bit more about that. All right, so let me dive into what I want to talk about. All right, so I'll talk about POD in a discrete setting and in a continuous setting. So please stop me if you have questions on the notation. I tried to make the notation nice, but it is what it is. So I'll be looking at a Hilbert space or multiple Hilbert spaces eventually. So this Hilbert space X can either be a continuous space. So, something for partial differential equations, the space of square integrable functions on some domain, or smoother functions. Or it can be, a finite dimensional Hilbert space, like a finite element space. With some inner product and norm. Okay. Then I'm going to have some positive scalar weights. So eventually we're going to think about those as quadrature, weights for approximating a time integral. And I'll get there. Okay. And we have this W super J will be our given data. That'll be the snapshots that we collect from some numerical method. Now, we could, again, we can think of this in a very continuous sense where we think about these WJs as exact, snapshots, infinite dimensional things, or they can be, finite element data, for example. Either one is fine. All right. So, all right, the pod problem is we want to find pod modes, which are an orthonormal basis for the Hilbert space. And we want to minimize some sort of data approximation error, right? That's what we're talking about. And so we want to, it's a sum of squares error with these quadrature weights. So the error between the snapshots and some projection of the snapshots. And R is typically, of course, low order. All right. And this is the standard orthogonal projection onto the span of the first R basis functions, and it's written there. So the inner product there, again, if you think of, the square integral functions, it's just the integral of these two functions, multiplied together or dot product or whatever. So yeah, all right. And again, if it's a finite element space of functions, it still, can be a, functional inner product, but it's computable, right? Okay, so, all right, and again, so what I'm going to look at here is going to look at this in terms of a singular value decomposition. So in a sense, pod and singular value decomposition are really the same thing. So in order to look at this, we'll take, if you remember, we have M of these snapshots, and we'll take RM, but we'll put a weight on the inner product. So the normal inner product is just the dot product, right, between two vectors, but I'll put a diagonal matrix gamma in between with those weights. All right, and again, we want to think of this as a discrete approximation to a time integral. Talk more about that later. So then we have the linear operator is defined there. So K, it takes a vector, an actual real vector, and maps into this Hilbert space. And it's a linear combination of the snapshot data multiplied by the weights and the components of this vector. So before I keep going, let me try and say something a little bit about notation. I'm going to attempt to use superscripts mostly to denote, as we do in numerical analysis with PDEs, with time stepping, right? I want to think about these as, denoting time steps. It does not have to, of course. So I'll use subscripts to denote counting things, typically. All right. So it really doesn't matter, but just helps to think about it that way. All right. So singular value decomposition of this operator. So that's a functional analytic thing. So maybe not often taught in a first course on functional analysis anymore. But it's, you don't have to think about it this way. You can think of the eigenvalue decomposition of that operator with its transpose and get the singular value decomposition that way. So in any case, and then it's a symmetric, compact operator, and you can get the eigenvalue decomposition. In any case, so singular value decomposition looks just like it does with the matrices. The formulas are there, and then you have this Hilbert adjoint, which takes something in your Hilbert space and maps it to a vector, and their formula is there. So just you take inner products. Oh, and I have a typo there. I'm sorry. It should be W. W's in the formula for the adjoint. W super 1 and so on. Sorry about that. Okay. But we won't need that so often. All right. So the solution of that data approximation problem is exactly the singular values of that operator K that are in the Hilbert space. So the singular vectors. So here vectors are understood as in the Hilbert space. All right. And we have an exact formula for this data approximation error. It's equal to the sum of the squares of the neglected singular values. So the idea, as you increase R, you hope, right, that often these singular values decay quickly to zero, and then this overall error decays quickly to zero as R increases, which then you hope you can use a low value of R to capture the data very well. All right. So a quick note here. We started this pod problem with a very specific low order rank R approximation to the data. That's not necessary. You can replace it with an arbitrary one and the solution remains the same actually. So, and again, there's many methods to compute these singular values and modes. Probably the most common one is the method of snapshots. As you start to deal with larger and larger scale data, then you do other things, randomized methods, incremental methods, and other things. I won't talk about those. So, all right, quickly, let me talk about continuous time. Right, so in this case, we'll have some interval, time interval, if you like. Really, it does not have to be a time interval. It can be some open set, in higher dimensions if you want, rather than one dimension, but I'll focus on time intervals here. Again, a Hilbert space, we want square integrable functions in time that take values in the Hilbert space. So now instead of, we had a sum of squares error before with those quadrature weights, if you will. So now we have just a time integral with the norm squared. So I hope you see the similarities there. Again, we have the same orthogonal projection there. And how do we get back and forth between them? You can take a left Riemann sum on this time integral and arrive back at that discrete pod problem. I won't go into the details. So that's how to connect them. And the weights there, if you do this specific thing, will be constant weights, always delta t, as if you have a constant time step. That's unnecessary, but I'll just look at it this way. So I tend to look at things this way. Probably due to my training, my PhD advisor, John Burns, who trained those. So I have maybe a bad habit of looking at things in the continuous setting and then trying to approximate down to the discrete setting. I tried to kind of reverse that recently and it's good to look at both sides because of course in the discrete setting, you actually can compute things. But as you start taking, limits, right? A finer time stuff, more and more data, you would ultimately like, just as in finite elements or any other numerical method, you want to understand the limiting behavior of whatever computations you do. So that's why I look at both of these things and sometimes connections between them. All right. The solution to the continuous time problem looks very similar. So again, as here, instead of a weighted, vector Rm space, it's going to be the space of square integrable functions on the time interval. And again, if you think back to what we had before in the discrete case, we had a weighted inner product, and that just comes from discretizing the time interval, roughly. All right. Again, I won't spend too much time there. So in this case, we have an integral operator for k, and the singular value decomposition works in the same way. All right. We need more theory to handle that one, but I won't deal with that. Okay. Pod modes, again, the singular vectors in the Hilbert space, the same approximation error formula we had before. This time we know the error tends to zero. Well, we knew that in the discrete case automatically because there could only be finitely many singular values in the discrete case. In the continuous case, we can have infinitely many positive singular values, but the error still must go to zero. And you can do collections of functions and more general rank R approximations. So I won't talk about that. Everything is the same. Okay. All right. So, why do we care about Hilbert spaces, different Hilbert spaces? Again, I know for many of you, this is, review, so please forgive me. I'll go through it quickly. So again, the heat equation or, diffusion equation, on a bounded domain, you have that the solution lives is square integrable in time, and it takes values in two different Hilbert spaces, L2 square integral functions on the domain or H10. There's two different inner products. And so you can measure these pod data approximation errors in different norms. And the numerical analysis for the diffusion equation or others, Navier-Stokes, both of these norms appear. All right. Sorry. Okay. The time weights I've indicated a little bit as we've gone through, right? So again, as you collect more and more snapshots, we would like to get some sort of convergence results. And Kudish and Volkwein worried about this in their second paper. And they looked at natural choices of the weights, as I've kind of been mentioning, and everything converges pretty nicely. So the data approximation errors converge, which is great. Okay, so all right, on to the actual data approximation errors and a little bit more on the recent history of this. So again, everything, the pod, the singular values, the modes, the data approximation errors depend on whatever Hilbert space you choose, and also whatever pod projection, right? We said at the beginning, we split the error in a certain way, we had a pod projection there. Okay, so Kudish and Volkwein in their papers, they found error bounds for the reduced order models that tended to zero under some certain assumptions when they took the stronger norm, right? The H10 norm for the pod computations, and they needed solution time derivative data. And that's something I'll come back to. So they didn't have these similar results, asymptotic results for the weaker Hilbert space, although they could see it in numerical experiments. So later, 10 years later, Chappelle and some others, they removed the need for this time derivative data in the same space, the stronger space, but they had to make some additional assumption concerning a family of pod projections. All right, and in both of these approaches, again, the pod projection used was different. Okay, so, all right. So I came into this looking at this a couple of years later, and I found some exact formulas for all of these different errors that you could look at. I looked at continuous time, and there's some error formulas that are different, not just involving the pod singular values or eigenvalues. This time they also involve the modes and sometimes the projections. And we could get nice asymptotic results, except in one case. The same case where we had this assumption on this family of pod projections. I couldn't get rid of that. I'll mention that. The pod projections, that will come up over and over. So Tryon and Julong, they dealt with the discrete case shortly after that, and again looked at the Navier-Stokes modified So, all right, I want to give a little bit of detail back on that paper because I'm going to build off of some of the ideas as I go forward. So, all right, so let me give I'll give some ideas for the continuous case. Forgive me, I'm going to jump back and forth between the continuous and discrete case as I go. I'll start with the continuous case. The discrete case is similar. If you see a time integral, just think of it as a sum and move on with life if you don't like the time integrals. So, all right, the idea here is we have two Hilbert spaces, just like with the heat equation or Navier-Stokes, right? L2 and H10 if you like. And we assume the data that we have lives in both of the Hilbert spaces, square integrable in time with values in both of these Hilbert spaces. All right. we're going to look at the pod problem for both H and V for different choices of the Hilbert space. And I'll use superscripts. The notation for this gets terrible. I didn't have this nice notation back in 2014. I think Stefan Volkbein came up with it later. Very nice superscript for the space, the pod space we use. So where we perform, what inner product we use for the pod computation. All right, so you know, if we put a super H on there, that means we used, you know, the H inner product, or the, you know, if you like, the L2 inner product for all the singular value decomposition computation. And I'll use lambda to denote the square of the singular values. Those are the pod eigenvalues, again, with the superscript denoting which space is used. There's in the continuous case, there's this annoying difference there's this technical difference between those eigenvalues and singular values when one is 0 and one is not. I will not deal with that. That bothered me for a few years. So, but it's just a technical detail. I'm not going to worry about it. All right. So there are 4, I would say, natural orthogonal pod projections that you can look at. And later I'll talk about non-orthogonal pod projections. So I'll have 2 sets of pod modes. You know, again, you can take the low order space of the pod modes that are constructed with the H inner product, I'll call that HR, or the low order space with the pod modes constructed with the V inner product, that's VR, right? So you can look at, right, orthogonal projections, you know, the most basic way you can think about them is a data approximation, right? That's how you construct them. You look at a given element of your Hilbert space, and you construct the element in your low order space that gives you the minimum norm error. Now the norm can change because we have 2 norms. So all right, so I'll use for the projections, I'll use P to when you're projecting onto the space HR, and Q when you're projecting on the VR. Which norm we are taking the minimization. All right. So you have all 4 of these projections, all of them can be computed. If you start to lose where we are and what we're doing, right? Just quickly here, if you think of H as the space of square integrable functions, right? And typically, you know, V is something like H10. So PRH is going to be your standard L2 projection. PRV is going to be like a Ritz projection or an elliptic projection. So then the Qs, right, are if you take if you look at the pod computations with H10 for the inner product, QRV is your standard. In that case, the orthogonal projection is again your Ritz projection or your elliptic projection, and QRH would be the L2 projection. All right, that's roughly how it goes, and everything behaves fine if you are in the right space. All of these are orthogonal. So if you look at the superscripts, if the spaces match, right? If you think of PRH mapping H to itself, it's orthogonal. PRV mapping V to itself, it's orthogonal. But of course, you can start dealing with these operators mapping on different spaces. And then in that case, they're still projections, but they're not orthogonal. And you start to lose a little bit of what you can understand about those things. So, all right, these are the known data approximation errors I wrote before. So just the sum of the neglected pod eigenvalues or squares of the singular values. All right. And here's where we get the new thing. So if you look at different projections and different norms, I won't go into a lot of details here. You get similar things. You get some of the neglected pod eigenvalues, but then they're multiplied by some additional terms involving how well you can approximate the pod modes with these projections in the wrong space. So if you see the, right, like the first one there, the first equality, you're looking at the pod modes constructed in the space H, but the projection is, in the using the space V, right? So, again, there's this mismatch. And it's the similar thing throughout. I won't go into all of these things. The nice thing, right? All these errors tend to zero, except in this one case that I mentioned earlier, where we have, in order to get the top convergence result there, you need this family of projections QRH to be uniformly bounded in the space of linear operators on V, right? So there's a mismatch there. In that case, right, those projections are not orthogonal anymore. And there's some supporting numerical evidence, but the theory is, as far as I know, out of reach. I keep going back to it every now and again. Yeah, no. All right. So, okay, as I said, so Tryon and Julong came a little later and did the discrete case. Quickly, let me just I'm not going to, this one slide, the proof idea in the discrete case is really nice. It's short, it's, so the idea is, if in the discrete case, there are only so many non-zero pod eigenvalues or singular values. I'll call those that number Sx. There's a finite number of them. So if you take the pod projection applied to the data instead of R, you use Sx, you get equality, right? And in that case, you get this nice exact expression for the error without any norms. You apply norms or different projections to this, and you use properties of inner products and pod eigenvalues and modes, and all those nice formulas come out. I won't go into details there. So that's very nice. Okay. I want to talk about 5 questions. So let's see. And we'll see how far I can go. All right. So first question. We talked about approximating the data that we started with. What else can we approximate? In particular, can we approximate all of those data approximation errors are sum of squares or time integral, errors. But can we approximate, for example, the data at a specific point in time or other data? So another thing for PDEs, numerical analysis, we don't necessarily want sum of squares norms or integral norms. We like to know, right, maximum norms, maximum errors in time. Third one, are the error bounds optimal in some way? I'll only mention that briefly. Another one, what happens if we deal with semi-norms or other operations applied to the data? I wasn't thinking about that at that time, but it came up later. And then I mentioned this already, and it never goes away, this last question. What about this uniform boundedness of these pod projections acting on the von Hilbert space? Now, and you can, I'll come back to what I mean there. So you can even ask that same question in the discrete setting, where in some sense, of course, they're uniformly bounded. But then the uniform bound may depend in some way badly on discretization parameters, right? So when I say uniform boundedness in the discrete setting, I really mean, is there a constant that is independent of the discretization parameters? Okay, still, we don't know that either. All right, so errors with semi-norms, briefly. My former PhD student, Yangwen Zhang, he did not work on reduced order modeling with me except for one paper. So he did hybridizable discontinuous Galerkin methods or HDG methods, and we did a lot of control problems and everything. And then he was interested. He's like, well, why don't we do pod and just for the heat equation to start? And that turned out to be terribly difficult, even to just derive the reduced order model in a way that made sense. Once we got there, doing the error analysis was also very tricky. We eventually got there. It's not perfect analysis, but we were in a spatially discrete setting, and we could, adapt that discrete pod argument. And here's one of the little results we had. So UH here is, your HDG solution, which is piecewise defined on some triangulation of the domain. So it's discontinuous in space. On each triangulation, though, it's nice, polynomial, or sorry, on each element. And we needed things like, divergence on each element, or gradient on each element, or even boundary traces of these things. And you could get them. And I hope you see something that looks very similar to the error formulas before. So instead of norms now, it's like this, we have some sort of semi-norms, right? And, as I had looked around, at other situations, the heat equation is nice, but there are many other PDEs where you're encountering all sorts of things in the error analysis, divergence curl, gradients, other projections that have nothing to do with pod. And then I'll mention inclusion operators and their inverses. I'll come back to that one in a second. There's many, many other things. And sometimes you could bound these things in terms of other quantities and get away with them, But anyway, another PhD student of mine, Sarah Locke, we looked at this. We thought, why not see what we can do here? And this was just a couple of years ago. We were able to deal with, operations or semi-norms applied to these, data approximation errors dealing with operators. And we were able to deal with certain types of non-orthogonal projections, which I'll mention. Okay. So I'll go through this quickly because the idea is similar. So we have discrete, I'll just look at the discrete case here. So again, we have some data in a Hilbert space X. And we have some linear operator mapping the data to some other Hilbert space Y. And these Hilbert spaces X and Y may have nothing to do with each other at all, right? You don't have to have one contained in the other or anything. Then you can have another projection mapping Y to itself, and this one does not need to be orthogonal. So for example, here, this one could be an elliptic projection coming from an asymmetric bilinear form. So something like this. So, all right. So the formulas look, I hope, kind of similar to before. I won't go through the details. So the main idea is you have various projections and linear operators applied to these things, and all the error formulas that we had before kind of push through in a nice way. All right. So maybe I'll indicate just quickly, I said this contains everything that we have done before. And the idea is to use inclusion or embedding operators and their inverses. So we had the two Hilbert spaces for the parabolic problem, H and V, right? With V contained in H, continuously embedded. So you can look at this operator L as, in some sense, a type of identity operator. I hate to call it identity because the identity operators we typically think of as mapping a space to itself, but these do not, right? They map either H to V or V to H. So they're more like embedding operators or inverses of these. So that's how you can get all the known results from before. Oops. I don't know. I'm not sure why there's a blue line there anymore, but it's okay. All right. So so these non-orthogonal projections acting on the wrong spaces are, in this case, are exactly equal to these kind of strange-looking projections, pod projections, that contain these compositions of different operators and projections. And again, the same problem we had. We didn't know if these things are uniformly bounded. And this question keeps coming up, and it keeps coming up in different scenarios, a lot of different people have looked at this, so I won't bother with that though. Okay, so that's one piece is, what can, we talked about all these data approximation error formulas. I want to talk a little bit about a different question. And that question is, what exactly can we approximate? So we know we can approximate the data. We know we can approximate in sum of squares or integral norms. But what else? And when we looked at that general framework, Sarah and I were able to kind of, I hope, get a good idea of what we can do. And the short story is you can approximate, you can approximate anything that's in the range of the pod operator, or sometimes in the range of this operator L. So again, in the discrete case, the pod operator is a linear combination of the snapshot data. So it's great. And so in some sense, you can approximate anything that's a linear combination of the data you started with. But the linear, how well you can approximate it depends on this vector G. So the coefficients in your linear combination. It also depends on those weights. So I'll give a couple just sample results here. So back in the setting of the parabolic PDs, not with L's and everything flying around everywhere. That's a little general. So in this setting, so we have the singular values, the sigmas, the singular vectors, which I'll call f sub j. Those are actual vectors, and this is the discrete case here. Well, they don't even have to be discrete case, but we'll just think of it as discrete case. Then you have the pod mode. So again, if you have things like any data y, this projection PRV, you can it'll converge to y. The PRV y will converge to y for anything in the range, and you get error bounds that are written there. The key in the error bounds, you will see things that maybe look familiar from these data approximation errors. They come back in these kind of local error bounds. So these projections acting on different pod modes, and there's all these mismatches. But then we have these Fourier coefficients, if you will, how well, the inner product of G with these singular vectors. And there's some other ones. I just put some examples here. And in different cases, you get different convergence results. For example, in that second case there, when you're taking, for example, if you do the pod computations with the H1 inner product and look at the L2 projection, things look pretty nice. You don't have any range condition. You get convergence everywhere. Of course, you don't know the speed of the convergence unless you look in the range. So maybe let me skip this. Well, I will mention just briefly. So I said that the speed of the convergence depends on this G, and you can kind of see this from this upper bound here in the last line. So you have this this first term in the parentheses is basically, how well G can be approximated by these singular vectors. And the second term is this data approximation error term. So it's kind of as a fixed term. Okay, so kind of the idea here is if G, so you're looking at things in the range of the pod operator. So some linear combination of the data you started with. And if those coefficients that give you this vector G is not well approximated by these singular vectors, then your convergence with these pod approximations, the pod projections the convergence may be slow. And so, I was really hoping to kind of get some more information here about what pod can do. But it maybe didn't tell us too much because we have to understand these other singular vectors, which is a trick. So, But this did tell us something about, I mentioned we want to talk about pointwise in time error bounds. But this gives us a clue that those are harder. So if you think about, if you want to know what happens to the data at a specific point in time, in the discrete case, in order to recover the data from the pod operator, you need your vector G to be 0 everywhere except a spike at that one point, right? And of course, we know that approximating such a thing with typically nice, smoothly varying vectors is not going to work very well, right? So that's a clue that pointwise time error bounds, even in the discrete case, may not work. And that's what we found later. And this is work with Trian and some others. But I believe maybe I will hit the highlights here and quit because I'm already 45 minutes in. So please excuse me while I flip forward a little bit. I'll get to the main points here. So you know, I mentioned, so people have been looking at these pointwise in time error estimates for all these reduced order models, and often this assumption was made here that the data at a specific point in time minus a projection of the data was bounded above by something nice. These pod error formulas that we have, and this constant C here is independent of your discretization parameters. Might depend on the final time of your time interval and so on. Okay, but you know, all that we just said indicates that this is probably unlikely to be true, and that going back to what we started with, right? Kunish and Volkwein had these time derivative data in there, or difference quotients, right? So yeah, so exactly what you would expect would happen. We did find counterexamples to this assumption. They're terrible counterexamples. They're maybe not natural, but they do exist, of course, right? We have some sort of, you know, spike like this that we have to deal with, right? Now, difference quotients, again, if you think back to this type of a range condition, if you have a pod operator that's made up of the data plus the time derivative, you can imagine you can recover the data at a specific point in time, right? And that's exactly what we were able to do, and we could get bounds like this when you include the difference quotients. We didn't end up using those bounds from my paper with Sarah. We did something much more straightforward. So did a discrete time Sobolev inequality, and we're able to get we're in the case of difference quotients, or if you think of time derivatives, whatever, we were able to get these bounds and get some optimality for these reduced order model error bounds for the heat equation, at least. So, and I will skip past, forgive me here. I wasn't sure how long I would take. So let me quickly summarize here. So I briefly looked at 5 questions, and some of these questions I looked at only very, very briefly, right? Did not really talk about the optimality of error bounds. Mentioned a little bit more about what can we approximate. Can we approximate at a specific point in time the data, semi-norms or operators applied? Yes, we can do that. And again, these uniform boundedness of these pod projections acting on the wrong Hilbert space, that came up again when we looked at the optimality of these pod error bounds, even when we had difference quotients. So we still could not get rid of those. They still come up. So let me at least mention a couple of recent works here. So on these difference quotients, pointwise in time error bounds, and other types of data approximation errors. So there's a few papers that are on archive looking at Berger's equation, Navier-Stokes. I'll mention the paper I did with Sarah Sarah Locke, now Sarah Eskew. We looked at the difference quotients and threw away all the snapshots except one, and kept the difference quotients. And you can get all the pointwise error bounds in the same way. And again, the basic idea is coming from either, if you want to think about it, these range conditions, or either a discrete time inequality, Sobolev inequality. Either way, that was the motivation there. You can, if you think about it in terms of ranges, it comes out pretty nicely. But this paper on the Navier-Stokes, more recent one, by Volker, John, and others, they took this modified procedure, and instead of using one snapshot plus the difference quotients, they took the time average of the data and the difference quotient. So of course, the time average, a lot of people use with pod, and they remove the time average, right? So then you only need the difference quotient. Anyway, so, and there's more work ongoing in all of these directions, and I think I will stop here. Thank you very much. Appreciate it. All right.
Very nice. Very nice. Excellent talk. Thank you, John. Are there any questions from the audience? So you can, unmute yourself and ask the question. If
go ahead.
If not, I will ask a question. So once while people warm up and they relax a little bit, maybe.
Can I ask a question? Can I?
Yeah, absolutely. Absolutely.
A very silly one. A very silly one. Probably you already mentioned it. But when you were talking about the continuous case, this operator capital K of U,
yes,
which was the integral on a certain interval of U times W, I didn't follow it, or maybe you mentioned this operator is compact, isn't it?
That's correct. And
but why should it be compact?
So why is it compact? So let me, that's great. Let me go back if I could. So I'll mention here in the discrete case, so I'll mention by analogy, but there's a little more. So in the discrete case, K here, if you think of this in the Frobenius norm or the Hilbert-Schmidt norm, okay, the Frobenius norm of K is exactly equal to the weighted sum of squares norm of your data.
Yes.
So in the continuous time case, it is the same. So there's some theory that says this operator is Hilbert-Schmidt. So it's in fact compact, right? And that the Hilbert-Schmidt norm of K is equal to the time integral of the norm squared of W. So that's your assumption that W is square integrable in time that takes values in X. And in fact, those two norms are the same. I believe there's even some isometry between these two spaces, all the Hilbert-Schmidt operators on spaces like this. So mapping an L2 space to a Hilbert space, there's an isometry between those Hilbert-Schmidt operators and these.
Yeah, but don't you need some assumption? Don't you need some assumptions on W?
Just that it is, well, Bachner integrable, right? Square integrable in time takes values in X. That's it. So the assumption is written up on the top there. So it in that Bachner space is the only assumption you need.
Okay.
So, yeah.
Thank you.
Yeah, sure. And I do have some in that paper I mentioned with Sarah Locke, the 2020 paper. We do the theory for that. So I had to dig out some old functional analysis for that one. But other people have noticed that connection before, but yeah.
Thank you.
Yeah, sure. That's a great question.
Other questions? Well, let me ask you maybe a quick question. So, John, when you talked about the discontinuous Galerkin method, you mentioned traces.
Yeah.
So how, I mean, just can you give us a flavor of what is involved? I mean, that's not the usual, you know, like continuous finite elements, you know, C0 type of finite element stuff. So
Correct. So I
well,
know
how does that how does that impact the POD? I'm just curious.
yeah, so for the HDG method, we looked at so it's a HDG works with a mixed formulation,
Mhm.
really a stabilized mixed formulation of the heat equation. So the standard thing is there are three variables. There's the solution. I've been calling it W, and I missed it. I put U here instead. So the solution of the heat equation, the flux, which is a vector valued, of course, unknown. So you don't approximate. You approximate the flux directly, and then unlike standard mixed methods, you approximate the trace of the solution on, so it's discontinuous, the solution, right? You have a triangulation of the domain. If you look on each element, you know, the solution U is polynomial there, and so it has a trace. But the solution U may be discontinuous across elements, so there's a trace on each element. And that is another unknown. So in U has a trace, but instead you approximate that directly. So we did that there, we computed three different pod basis functions: the state, the flux, and the trace on the skeleton of the mesh. And yeah, so that was the idea. Yeah, so you could do all sorts of interesting things like that. And it turns out, I think I didn't, you know, when you look at the trace, that was the tricky one. And at the time, I wondered why the pod singular values were much larger for the trace. And I realized later we did not scale the norm properly. So we missed a copy of H or something like that in the norm. I mean, it still worked fine because it was discrete, but if you put an H in there, the norm for the trace kind of scales in the same way as the other norm. So yeah, that's just an idea. Yeah.
Very nice, thank you.
Sure.
Any other questions? So, okay, maybe I can ask another question quickly. Sure. So I really like that you brought this up, the idea of projections and the assumptions that need to be made about these different projections. And so any feel for, so I mean, you pointed out that right now this is still an open question, and I was wondering whether you have any idea of, I mean, it looks like it's an important ingredient, and any idea of how to move forward with this? You said that in some cases it's valid, but maybe in other cases it's probably not valid. So any insight into how we need to proceed?
Yeah, let me pull these up. So I wish I had something, but no. Unfortunately, I have no insight. All of the numerical evidence that I know of tends to indicate that these things are uniformly bounded.
Right.
However, that was most of the numerical evidence we had also for the pointwise and time error estimates as well, which behave properly most of the time, right? And we had to construct some kind of bizarre counterexamples, right? And we still don't know in practice, right? This talk was, of course, on the theoretical side. We still don't know in practice if that matters, right? So it could be that in practice, these things are almost always uniformly bounded, but there may be some strange counterexample. I tried, I looked quite a lot at, non-orthogonal projections, just the general theory and stuff like this. I found one reference to something where there was a family of non-orthogonal projections, not pod, something else, where uniform boundedness was true in one space, but not in another.
Okay.
And it wasn't even a paper. I mean, it was some, little offhand remark somebody made. I was like, oh, come on, give me a reference. So I really don't know. And probably my suspicion is, okay, you asked me my guess is that in practice, you probably won't see this, any issues. In the numerical analysis, okay, what can we do, right? We said, okay, if everything is discrete, yes, these things are uniformly bounded by some, something like H inverse or, some constant times H inverse. And then that may lead to some restrictions in your error analysis or some suboptimality. That may be what we get in, without some sort of, other assumption, but I've tried. I messed with this quite a lot, probably way too much, unfortunately.
Thank you. Thank you. This was an excellent answer. Thank you. Questions? Any other questions? Okay, I don't see any raised hands, but I can ask one final question, and this is more general. So
Sure.
You also said, John, in your talk that, somehow that's how you started, and I agree with that somehow, it's been the numerical analysis for POD, which is, I think, arguably, but maybe the most used reduced order modeling technique in like currently in various fields. But the numerical analysis is relatively young, like 20 years or so. And you said that it would be nice if the numerical analysis for POD would get to a similar level. And I was just wondering whether you have, and you can just answer no, and but any guess, what's your gut feeling? So are we getting there? How long is it gonna take? Are we never gonna be there? What's your estimates? Guesstimate.
That's really hard, because I think the answer to that question really depends on, so I view pod, okay, so we live in the age of data science, right? And often with data science, we have, algorithms that are trained, and then, of course, we use them on data where we did not train, right? And often in that case, we lose guarantees there. So in some sense, I view pod in the same way. It's a method that's based on training. You train in the sense you have some data, you train and you construct your modes, and you construct your reduced order model, but you want to use it outside of the training set. And at this point in time, I feel we're kind of a far way away from understanding how well we can approximate that data that is outside of the training set. And I guess that's why a long time ago, I started looking even at all these weird questions. I really hoped that maybe I could get some insight into that question. And I'm not sure that I have. So I would say we, barring some breakthrough there, we may be a far way away. However, I still think these things have uses in the sense of, okay, often we don't stray too far away from the training set. And we want to say, all right, maybe at least these numerical analysis results tell us something about what we expect. And maybe that's the best we can do. But maybe that's in many cases good enough. Or in some cases, we may be able to, use some other techniques like with optimization, trust regions, and so on to get something very useful, right? So there may be something very specific where the numerical analysis helps. So I'm not sure I know the answer. I'm interested enough, I'm going to keep hacking away at this stuff, I guess.
Great, great. Thank you. That was an excellent answer. I agree completely with everything you said, including maybe numerical analysis can be used, to give us some ideas, some practical ideas, and then take it in a different direction, maybe something that we haven't thought about before. So I completely agree. So like a guide, I think that's a good point. Well, anyway, so thank you, John.
Yeah, sure.
Any other questions from the audience? If not, if you want, I'm sure that John would be happy to answer your questions by email. We're gonna post this on the talk on YouTube, and please reach out to John if you have any question. I will reach out to John as always, because I have more questions. But if no more questions, then let's thank John again, and we'll see everyone next week when Professor Yano will give the next NAGROMS seminar. So looking forward to that. Thank you, John.
All right, thank you all. Appreciate you coming.